We then stringify the result. Such a job is often for analytical purposes, where data is exported from a production database and stored elsewhere for processing later. The production database is most often, depending on the data model, not capable of returning historical data. For example, the state of the database as it was 1 month ago. Therefore, a periodic export is often created and stored for later processing. Historic data dumps will grow your storage requirements quickly and require distributed processing to crunch all data. In this section, we'll explore how to orchestrate such a task with Airflow. We've developed a GitHub repository with code examples to go along with this book. It contains a Docker Compose file for deploying and running the next use case, where we extract Airbnb listings data and process it in a Docker container with pandas. In a large-scale data processing job, the Docker container could be replaced by a Spark job, which distributes the work over multiple machines. The Docker Compose file contains the following: 1 Postgres container holding the Airbnb Amsterdam listings, 1 AWS S3 API compatible container. Since there is no AWS S3 in Docker, we created a minio container, AWS S3 API compatible object storage, for reading, writing data. 1 Airflow container. Visually, the flow will look like figure 7.12. Airflow acts as the spider in the web, starting and managing jobs and ensuring all finish successfully in the correct order, failing the pipeline if not. The Postgres container is a custom-built Postgres image holding a database filled with inside Airbnb data available on Docker Hub as Airflow Book inside Airbnb. The database holds one single table named Listings, which contains records of places in Amsterdam listed on Airbnb between April 2015 and December 2019, figure 7.13. Let's first query the database and export data to S3. From there, we will read and process the data with pandas. A common task in Airflow is a data transfer between two systems, possibly with a transformation in between. Querying a MySQL database and storing the result on Google Cloud Storage, copying data from an SFTP server to your data lake on AWS S3, or calling an HTTP REST API and storing the output have one thing in common, namely that they deal with two systems, one for the input and one for the output. In the Airflow ecosystem, this has led to the development of many such A to B operators. For these examples, we have the MySQL to Google Cloud Storage operator, SFTP to S3 operator, and the simple HTTP operator. While there are many use cases to cover with the operators in the Airflow ecosystem, there is no Postgres query to AWS S3 operator at the time of writing this book. So, what to do? Section 7.2.1. Implementing a Postgres to S3 operator. First, we could take note of how other similar operators work and develop our own Postgres to S3 operator. Let's look at an operator closely related to our use case. The Mongo to S3 operator in airflow.providers.amazon.aws.transfers.mongo_to_S3 after installing Apache Airflow Providers Amazon. This operator runs a query on a MongoDB database and stores the result in an AWS S3 bucket. Let's inspect it and figure out how to replace MongoDB with Postgres. The execute method is implemented as follows. Some code was obfuscated. It's important to note that this operator does not use any of the file systems on the Airflow machine, but keeps all results in memory. The flow is basically: since this operator keeps the intermediate results in memory, think wisely about the memory implications when running very large queries, because a very large result could potentially drain the available memory on the Airflow machine. For now, let's keep the Mongo to S3 operator implementation in mind and look at one other A to B operator, the S3 to SFTP operator. This operator, again, instantiates two hooks, SSH hook, SFTP is FTP over SSH, and S3 hook. However, in this operator, the intermediate result is written to a named temporary file, which is a temporary place on the local file system of the Airflow instance. In this situation, we do not keep the entire result in memory, but we must ensure enough disk space is available. Both operators have two hooks in common, one for communicating with System A and one for communicating with System B. However, how data is retrieved and transferred between systems A and B is different, and up to the person implementing the specific operator. In the specific case of Postgres, database cursors can iterate to fetch and upload chunks of results. However, this implementation detail is not in the scope of this book. Keep it simple and assume the intermediate result fits within the resource boundaries of the Airflow instance. A very minimal implementation of a Postgres to S3 operator could look as follows. Let's inspect this code. The initialization of both hooks is straightforward. We initialize them, providing the name of the connection ID the user provides. While it is not necessary to use keyword arguments, you might notice the S3 hook takes the argument AWS_con_ID and not S3_con_ID as you might expect. During the development of such an operator and the usage of such hooks, it is inevitable to sometimes dive into the source code or carefully read the documentation to view all available arguments and understand how things are propagated into classes. In the case of the S3 hook, it subclasses the AWS hook and inherits several methods and attributes, such as the AWS_con_ID. The Postgres hook is also a subclass, namely of the DB API hook. By doing so, it inherits several methods, such as get_records, which executes a given query and returns the results. The return type is a sequence of sequences, more precisely a list of tuples. We then stringify the results and call load_string, which writes encoded data to the given bucket key on AWS S3. You might think this is not very practical, and you are correct. Although this is a minimal flow to run a query on Postgres and write the result to AWS S3, the list of tuples is stringified, which no data processing framework is able to interpret as an ordinary file format, such as CSV or JSON, figure 7.14. Footnote 6. As specified in PEP 249, the Python Database API specification. The tricky part of developing data pipelines is often not the orchestration of jobs with Airflow, but ensuring all bits and pieces of various jobs are configured correctly and fit together like puzzle pieces. So, let's write the results to CSV. This will allow data processing frameworks such as Apache Pandas and Spark to easily interpret the output data. For uploading data to S3, the S3 hook provides various convenience methods. For file-like objects, we can apply file_obj. Footnote 7. In-memory objects with file operation methods for reading, writing. Buffers live in memory, which can be convenient because memory leaves no remaining files on the file system after processing. However, we have to realize that the output of the Postgres query must fit into memory. The key to idempotency is setting replace equals true. This ensures existing files are overwritten. We can rerun our pipeline after, for example, a code change, and then the pipeline will fail without replace equals true because of the existing file. With these few extra lines, we can now store CSV files on S3. Let's see it in practice. With this code, we now have a convenient operator that makes querying Postgres and writing the result to CSV on S3 an exercise in filling in the blanks. Section 7.2.2. Outsourcing the heavy work. A common discussion in the Airflow community is whether to view Airflow as not only a task orchestration system, but also a task execution system, since many DAGs are written with the Bash operator and Python operator, which execute work within the same Python runtime as Airflow. Opponents of this mindset argue for viewing Airflow only as a task triggering system and suggest no actual work should be done inside Airflow itself. Instead, all work should be offloaded to a system intended for dealing with data, such as Apache Spark. Let's imagine we have a very large job that would take all resources on the machine Airflow is running on. In this case, it's better to run the job elsewhere. Airflow will start the job and wait for it to complete. The idea is that there should be a strong separation between orchestration and execution, which we can achieve by Airflow starting the job and waiting for completion, and a data processing framework such as Spark performing the actual work. In Spark, there are various ways to start a job. Using the Spark submit operator. This requires a Spark submit binary and yarn client config on the Airflow machine to find the Spark instance. Using the SSH operator. This requires SSH access to a Spark instance, but does not require Spark client config on the Airflow instance. Using the simple HTTP operator. This requires running Livy, a REST API for Apache Spark, to access Spark. The key to working with any operator in Airflow is reading the documentation and figuring out which arguments to provide. Let's look at the Docker operator, which starts the Docker container for processing the inside Airbnb data using pandas. The Docker operator wraps around the Python Docker client and, given a list of arguments, enables starting Docker containers. In listing 7.15, the Docker_URL is set to a Unix socket, which requires Docker running on the local machine. It starts the Docker image Airflow book/number cruncher, which includes a pandas script loading the inside Airbnb data from S3, processing it, and writing back the results to S3. Airflow manages the starting of the container, fetching logs, and eventually removing the container if required. The key is to ensure no state is left behind such that your tasks can run idempotently and no remainders are left. Summary. Operators for external systems expose functionality by calling the client for a given system. Sometimes these operators are merely passing through arguments to the Python client. Other times they provide additional functionality, such as the SageMaker training operator, which continuously pulls AWS and blocks until completion. If access to external services from the local machine is possible, we can test tasks using the CLI command airflow tasks test. Chapter 8. Building Custom Components. This chapter covers making your DAGs more modular and succinct with custom components, designing and implementing a custom hook, designing and implementing a custom operator, designing and implementing a custom sensor, distributing your custom components as a basic Python library. One strong feature of Airflow is that it can be easily extended to coordinate jobs across many different types of systems. We have already seen some of this functionality in earlier chapters, where we were able to execute a job for training a machine learning model on Amazon's SageMaker service using the S3 copy object operator. But you can, for example, also use Airflow to run jobs on an ECS, Elastic Container Service, cluster in AWS using the ECS operator to perform queries on a Postgres database with the Postgres operator and much more. However, at some point, you may want to execute a task on a system that is not supported by Airflow, or you may have a task that you can implement using the Python operator, but that requires a lot of boilerplate code, which prevents others from easily reusing your code across different DAGs. How should you go about this? Fortunately, Airflow allows you to easily create new operators for implementing your custom operations. This enables you to run jobs on otherwise unsupported systems, or simply to make common operations easy to apply across DAGs. In fact, this is exactly how many of the operators in Airflow were implemented. Someone needed to run a job on a certain system and built an operator for it. In this chapter, we will show you how you can build your own operators and use them in your DAGs. We will also explore how you can package your custom components into a Python package, making them easy to install and reuse across environments. Section 8.1. Starting with a Python operator. Before building any custom components, let's try solving our problem using the, by now familiar, Python operator. In this case, we're interested in building a recommender system, which will recommend new movie or movies to watch depending on our view history. However, as an initial pilot project, we decide to focus on simply getting in our data, which concerns past ratings of users for a given set of movies and recommending the movies that seem most popular overall based on their ratings. The movie ratings data will be supplied via an API, which we can use to obtain user ratings in a certain time period. This allows us, for example, to fetch new ratings daily, and to use this for training our recommender. For our pilot, we want to set up this daily import process and create a ranking of the most popular movies. This ranking will be used downstream to start recommending popular movies. Figure 8.1. Section 8.1.1, Simulating a Movie Rating API. To simulate data for this use case, we use data from the 25M Movie Lens dataset. See this link, which is freely available and contains 25 million ratings for 62,000 movies by 162,000 users. As the data itself is provided as a flat file, we build a small REST API using Flask, which serves parts of the dataset at different endpoints. Footnote 1. The code for the API is available in the code repository accompanying this book. To start serving the API, we've provided a smaller Docker Compose file that creates multiple containers, one for our REST API and a couple for running Airflow itself. You can start both containers using the following commands. After both containers have finished starting up, you should be able to access our movie rating API at port 5000 on localhost. See this link. Visiting this URL should show you a hello from our movie rating API, figure 8.2. For this use case, we are mainly interested in obtaining movie ratings, which are provided by the /ratings endpoint of the API. To access this endpoint, visit http://localhost:5000/ratings. This should result in an authentication prompt, figure 8.3, as this part of the API returns data that could contain potentially sensitive user information. By default, we use Airflow/Airflow as a username and password combination. After you enter the credentials, you should get an initial list of ratings, figure 8.4. As you can see, the ratings are returned in a JSON format. In this JSON, the actual ratings are contained in the result key, while two additional fields, limit and offset, indicate that we are only looking at a single page of the results, the first 100 ratings, and that there are potentially more ratings available, indicated by the total field, which describes the total number of records available for a query. To step through the paginated result of a query, you can use the offset parameter of the API. For example, to fetch the next set of 100 records, we can add the offset parameter with a value of 100. http://localhost:5000/ratings?offset equals 100. We can also increase the number of records retrieved in a single query using the limit parameter. http://localhost:5000/ratings?limit equals 1000. By default, the ratings endpoint returns all ratings available in the API. To fetch ratings for a specific time period, we can select ratings between a given start and date using the start_date and end_date parameters. Footnote 2. The API only goes back 30 days, so make sure to update the start and date parameters to more recent dates than this example to get results. http://localhost:5000/ratings?start_date equals 2019-01-01 &end_date equals 2019-01-02. This API filtering functionality will allow us to load data from the API on an incremental, daily basis, without having to load the full dataset. Section 8.1.2, Fetching Ratings from the API. Now that we've seen the basics of the Movie Lens API, we want to start fetching ratings programmatically so that we can later automate this fetching using Airflow. For accessing our API from Python, we can use requests. See this link, which is a popular and easy-to-use library for performing HTTP requests in Python. To start firing requests at our API, we first need to create a requests session using the session class. This session will then allow us to fetch ratings from our API by using its GET method, which performs a GET HTTP request on our API. The GET method also allows us to pass extra arguments, such as parameters, for example, start, end date, to include in the query. Our call to GET will return a response object representing the result of the request. This response object can be used to check whether the query was successful using the raise_for_status method, which raises an exception if the query returned an unexpected status code. We can access the result of the query using the content attribute, or in this case, using the JSON method, as we know that our API returns JSON. If we perform this query, we should see that our requests fail, as we forgot to include any authentication in our request. Because our API is using basic HTTP authentication, we can configure our session to include our authentication details as follows. This will make sure that the requests session includes our username, password authentication with its requests. Let's encapsulate this functionality in a _get_session function, which will handle setting up the session with authentication so that we don't have to worry about this in other parts of our code. We'll also let this function return the base URL of the API so that this is also defined in a single place. To make this a bit more configurable, we can also specify our username, password, and the different parts of our URL using environment variables. This will later allow us to easily change these parameters when running our script by defining values for these environment variables. Now that we have a rudimentary setup for our request session, we need to implement some functionality that will transparently handle the pagination of the API. One way to do this is to wrap our call to session.get with some code that inspects the API response and keeps requesting new pages until we reach the total number of rating records. By using yieldFrom to return our results, this function effectively returns a generator of individual rating records, meaning that we don't have to worry about pages of results anymore. Footnote 3. An additional advantage of this implementation is that it is lazy. It will only fetch a new page when the records from the current page have been exhausted. The only thing missing is a function that ties this all together and allows us to perform queries to the ratings endpoint while specifying start and end dates for the desired date range. This provides us with a nice, concise function for fetching ratings, which we can start using in our DAG. Section 8.1.3, Building the Actual DAG. Now that we have our _get_ratings function, we can call it using the Python operator to fetch ratings for each schedule interval. Once we have the ratings, we can dump the results into a JSON output file, partitioned by date so that we can easily rerun fetches if needed. We can implement this functionality by writing a small wrapper function that takes care of supplying the start-end dates and writing the ratings to an output function. Note that the start_date, end_date, output_path parameters are passed using templates_dict, which allows us to reference context variables, such as the execution date, in their values. After fetching our ratings, we include another step, rank_movies, to produce our rankings. This step uses the Python operator to apply our rank_movies_by_rating function, which ranks movies by their average rating, optionally filtering for a minimum number of ratings. This results in a DAG comprising two steps, one for fetching ratings and one for ranking movies. As such, by scheduling this DAG to run daily, it provides a ranking of the most popular movies for that day. Of course, a smarter algorithm might take some history into account, but we have to start somewhere, right? Section 8.2, Building a Custom Hook. As you can see, it takes some effort and code to actually start fetching ratings from our API and to use them for our ranking. Interestingly, the majority of our code concerns the interaction with the API, in which we have to get our API address and authentication details, set up a session for interacting with the API, and include extra functionality for handling details of the API, such as pagination. One way of dealing with the complexity of interacting with the API is encapsulating all this code into a reusable Airflow hook. By doing so, we can keep all the API-specific code in one place and simply use this hook in different places in our DAGs, which allows us to reduce the effort of fetching ratings to something like this. Hooks also allow us to leverage Airflow's functionality for managing connection credentials via the database and UI, meaning that we don't have to manually supply our API credentials to our DAG. In the next few sections, we'll explore how to write a custom hook and set about building a hook for our movie API. Section 8.2.1, Designing a Custom Hook. In Airflow, all hooks are created as subclasses of the abstract base hook class. To start building a hook, we need to define a dunderInit method that specifies which connection the hook uses, if applicable, and any other extra arguments our hook might need. In this case, we want our hook to get its connection details from a specific connection, but don't need any extra arguments. Most Airflow hooks are expected to define a get_con method, which is responsible for setting up a connection to an external system. In our case, this means that we can reuse most of our previously defined _get_session function, which already provides us with a pre-configured session for the movie API. That means a naive implementation of get_con could look something like this. However, instead of hard-coding our credentials, we prefer to fetch them from the Airflow credentials store, which is more secure and easier to manage. To do so, we first need to add our connection to the Airflow metastore, which we can do by opening the Admin Connections section using the Airflow web UI and clicking Create to add a new connection. In the Connection Create screen, figure 8.5, we need to fill in the connection details of our API. In this case, we'll call the connection MovieLens. We'll use this ID later in our code to refer to the connection. Under connection type, we select HTTP for our REST API. Under host, we need to refer to the host name of the API in our Docker Compose setup, which is MovieLens. Next, we can optionally indicate what schema we'll use for the connection, HTTP, and add the required login credentials, user, Airflow, password, Airflow. Finally, we need to say under which port our API will be available, which is port 5000 in our Docker Compose setup, as we saw earlier when manually accessing the API. Now that we have our connection, we need to modify our get_con to fetch the connection details from the metastore. To do so, the basehook class provides a convenience method called get_connection, which can retrieve the connection details for a given connection ID from the metastore. This connection configuration object has fields that map to the different details we just filled in when creating our connection. As such, we can use the config object to start determining the host port and user password for our API. First, we use the schema host and port fields to determine our API URL as before. Note that we define default values in our class, similar to the constants we defined before, in case these fields are not specified in the connection. If we want to require them to be specified in the connection itself, we can raise an error instead of supplying defaults. Now that we have obtained our base URL from the metastore, we only need to configure authentication details in our session. This gives us the following new implementation for get_con. One drawback of this implementation is that each call to get_con will result in a call to the Airflow metastore, as get_con needs to fetch the credentials from the database. We can avoid this limitation by also caching session and base_URL on our instance as protected variables. This way, the first time get_con gets called, self._session is none. So we end up fetching our connection details from the metastore and setting up our base URL and session. By storing these objects in the _session and _base_URL instance variables, we make sure that these objects are cached for later calls. As such, a second call to get_con will see that self._session no longer is none, and will return a cached session and base URL. Note: personally, we're not fans of using the get_con method directly outside of the hook, even though it is publicly exposed, because this method exposes the internal details of how your hook accesses the external system, breaking encapsulation. This will give you substantial headaches if you ever want to change this internal detail, as your code will be strongly coupled to the internal connection type. This has been an issue in the Airflow codebase as well. For example, in the case of the HDFS hook, where the implementation of the hook was tightly coupled to a Python 2.7 only library, Snakebite. Now that we have completed our implementation of get_con, we are able to build an authenticated connection to our API. This means we can finally start building some useful methods into our hook, which we can then use to do something useful with our API. For fetching ratings, we can reuse the code from our previous implementation, which retrieved ratings from the /ratings endpoint of the API and used our get_with_pagination function to handle pagination. The main difference from the previous version is that we now use get_con within the pagination function to get our API session. Altogether, this gives us a basic Airflow hook that handles connections to the Movie Lens API. Adding extra functionality, other than just fetching ratings, can be easily done by adding extra methods to the hook. Although it may seem like a lot of effort to build a hook, most of the work was shifting around the functions we wrote before into a single consolidated hook class. An advantage of our new hook is that it provides nice encapsulation of the Movie Lens API logic in a single class, which is easy to use across different DAGs. Section 8.2.2 Building our DAG with the Movie Lens hook. Now that we have our hook, we can start using it to fetch ratings in our DAG. However, first we need to save our hook class somewhere so that we can import it into our DAG. One way is by creating a package in the same directory as our DAG's folder and save our hook in a hooks.py module inside this package. Footnote 5. We'll show another package-based approach later in this chapter. Once we have this package, we can import our hook from the new custom package, which contains our custom hook code. After importing the hook, fetching ratings becomes quite simple. We only need to instantiate the hook with the proper connection ID, and